So now I can say apologies to Juan. Forgot to record. Let's see, we've been going through chapter 3.3 and we've come to this piece of magic here that psi, shoot, sorry about that. Psi represents some state. Each object like this represents a state of a system. In general, if you act with an operator on a state, you do not get the same state back. You get a different state. But there are some magical states, let's call them psi sub k, for which, when acting with that operator on that state, it leaves the state changed only by a complex scalar. And those are called the eigenstates, and those are called the eigenvalues corresponding to the eigenstates. And what we found here is that Hermitian operators have real eigenvalues, and so those are the things that can correspond to observables. And also another theorem, eigenfunctions belonging to discrete eigenvalues are orthogonal. And so if say H acting on psi1 is E1 psi1, and H acting on psi2 is E2 psi2, and E1 is not equal to E2, then psi1 is orthogonal to psi2. And the next theorem is that the eigenfunctions of Hermitian operators are complete. They span the Hilbert space. So that is sort of said here that for any member of a Hilbert space, we can write that member of a Hilbert space equal to itself, but stick next to it the identity operator, which I didn't quite have room to squeeze in. And so when we stick in the identity operator, remember summation convention, this is a sum. And so this thing here is just an inner product. One way to think of it is it's the projection of psi onto psi sub k, the basis function psi k, or its dual. And that's just going to be some complex number. And so we can write that as some ck times psi k. Remember, we're summing over k. What is a wave function? Usually when we talk about a wave function psi of x, we are talking about the projection of psi in the x basis. And sometimes we talk about momentum wave functions, which is the projection of state psi in the p basis. And these x's and p's again represent states that span the Hilbert space. Okay, so let's look at some examples. So if we look at the eigenfunctions of P, the momentum operator. Oh, and the other thing we looked at is that d by dx is anti-Hermitian because the complex conjugate, or d by dx acting on a dude here, is equal to the minus, let me put it this way, put it right in here. So so if q equals d by dx, okay, then we can look at some state A and Q acting on B. And if we want to move Q over here and we take a dagger, then what we find is that Q, first of all, what is Q dagger? Well, it's the complex conjugate of this, which is the same thing. And if we do that, this is not true. There's a minus sign stuck in there. That putting Q on the other side gives us a minus sign. And it's anti-Hermitian, but Q or Q1, Q2 equals I d by dx is Hermitian. Because when you move the I to the other side, you get another negative, which kills that one. And so is anti. And so this being anti-Hermitian means that d by dx is not an observable. But I times d by dx is, or could be, an observable because observables have to be Hermitian. This operator has real eigenvalues. This one does not. Okay, so let's see. Example 3.2 in Griffith, eigenfunctions of the momentum operator. We're looking for what kinds of functions is it that minus IH bar d by dx acting on a function is equal to a constant times that function. And the answer, again, you can guess it, is that functions of the form AE to the minus IPX over H bar satisfy that equation. And so these are complex exponentials. And if you want to think of this using Euler's theorem, right, that's a cosine of px over h bar minus I sine px over h bar. And so these are functions that oscillate in, you know, in the imaginary, well, oscillate in x, right? With frequency, you know, k, or wave number, k equals, or p equals h bar k. So, so we can also normalize these buggers, and there's the normalization that'll get them orthonormal. And to show that, again, each one that has a different value of p, according to the theorem, are orthogonal. And we can show that because if we integrate two of these functions, psi p, take the inner product of psi p and psi p prime, that's going to equal e to the ix over h bar p minus p prime dx. And this thing is a delta function. It's a direct delta function. And that's a definition of orthogonal. So the eigenfunctions of p are sinusoidal with wavelength 2 pi h bar over p. That's the old de Broglie formula. Oh, where'd that come from?
Direct delta is the sum killer?
Direct delta, well, this one is the integral killer, right?
So you can't take the integral, or, well, the integral of the direct delta is one, right?
So
Yeah.
that means direct delta is the
Yeah.
that one? It's the
Yeah.
weird one where it's like infinity at some point
Yeah.
or everywhere else.
It's infinity at one point, and then it's just zero everywhere else. It kind of looks like that.
Hey, I'm going to show you something that I think will blow your mind. All right, here, let me clear my workspace. A equal,
Physicists that come up with
how about zeros, 1,000 comma 1? Okay, so I got 0 or 1,000 zeros and a 500 equal 1. Okay, how's that for a direct delta?
No.
No?
Well, it has to be greater than one.
Sum of A.
I mean.
Okay,
Ah,
okay,
close enough.
close enough, all right, what's a
Well,
Fourier?
that's the thing, it's too discretized for something like this. You can't have, because it's not saying that there's, because when you have.
Hey,
it
I'm
as-
in discrete, I'm in sampling space,
Would you-
okay?
Yeah,
Would you be happier if it was
It's a
10
s-
billion instead of 1,000 points?
well,
I'm
even
saying,
if
let
it's-
me just say, it doesn't matter if I made it 10,000, okay?
Yeah,
Doesn't matter, okay? I mean, to within normalization. Now, my next question is FA is FFT of A, right? What does FA look like? What's a
Fourier
spectrum?
transform. Would just be,
There's A,
yeah,
all right? So delta function. You ready? Gotta plot the absolute value of FA,
yeah, that's gonna.
constant. Every frequency equally represented. I mean, really freaking constant.
How does that work?
Because in order to create a delta function, here, let me go back the other way.
Mhm.
A equals sine of,
Sine.
2 times pi times, 0 to, 1,000. So that's X over, okay, we'll make like 10 periods or something like that, or 100, or yeah, 10 periods, right? So when X or when T is 1,000, then this thing is 10, okay?
Mhm.
So I should have called this B. And so let's see what we did. Plot A. Okay, so there are 10 periods of sine wave.
Mhm.
Okay, what's the FFT of A? The delta function.
Um. Yeah, I guess it is a delta. It's not a direct delta, but. It's a delta.
Now, the reason that you're seeing two of these is that there's a negative frequency over there, right? So
Where does that come from?
this is a mirror. Where does it come from? Here, let's do a spectrum. Amplitude spectrum, because this thing normalizes. A spectrum of A comma, let's say we sampled at 100 hertz. Okay.
Mhm.
Now you could say, huh, to that, but here, let me do one more thing. A 1 to n minus 1, because I have an extra data point in there. Oops,
No, you need to subtract one of that.
there we go. So that's a delta function. Right, now this is on a log scale, right? And so you can see here dots, okay, so you can see that it's got, an amplitude of 1 and everything else is like doodly squat, right? Zeros. So a sine wave, the Fourier transform of a sine wave in frequency space is a delta function.
Yeah.
Write it
Oh.
over here.
So.
If we take a sine wave in time and we do an FFT, we get a delta omega minus omega naught
Mhm.
in frequency domain, right? If we take,
Wait, what are we FFTing it? Are we FFTing it with another function? Or
no,
with
just FFTing over time, right?
over the function of time.
Over time being the
Oh.
independent variable. So the FFT here is the integral, here is, call it V of t. So the integral 0 to capital T, V, I guess 1 over T's, V of t e to the minus I omega t dt. That's our Fourier transform. So it killed t, right? T went out, t got integrated away, and it left me with omega. And for different values of omega, I get 0, 0, 0, 0, bloop, 0, 0, 0, 0, right? And which omega do I get? The omega corresponding to this bugger.
Yeah.
Okay. Now, what about in the time domain when I have bloop, v of t equal delta of t minus t naught? That's a delta. Okay, so what is his Fourier transform? And you just saw it. There's a Fourier transform. Amplitude is a function of omega. It's constant. Yeah, sorry.
Why?
So it takes all frequencies
Yeah.
to build this. If you don't have all frequencies, you can't build that kind of discontinuity.
So I guess for an instant, a super drastic increase and super drastic decrease, you would need.
The best case that you're thinking of is the Gaussian.
We can't see, by the way.
Oh, sorry. So beautiful Gaussian here. V of t,
Like a distribution.
yeah, V of t is some, you know, a e to the minus t squared over 2 sigma squared. Okay. And what's the Fourier transform of a Gaussian?
I really should know this. Why don't I know this?
Yeah, I feel like I'm lacking on some knowledge.
Well, because I'm in statistics, so that's
Oh.
like, Gaussian is huge in statistics.
Yeah.
That's why I'm like, I should know this. I don't know why I don't know this.
And I'm trying to think, what I want to say is it's a Gaussian, or A of omega is equal to, you know, again, some normalization, A naught e to the minus omega squared over 2 sigma squared
That's the Fourier transform.
of the Gaussian is a Gaussian.
Transformation
Okay.
of Gaussian.
And
Oh, okay. So if you squeeze it.
Yeah, it's another Gaussian function.
yeah.
Okay.
So where this is sort of
Which-
super important
Yeah.
in like practically, you know, in electronics is if I have noise that if I have a signal, say, at frequency omega naught, and I want to characterize the signal and it's contaminated with noise, then the Fourier transform is a powerful way to concentrate all my signal into one tiny little region of frequency space. And then I can say, okay, here's my signal, and I'm going to ignore all these other amplitudes because I'm not interested. And so this is why the Fourier transform is used so much in signal processing to get the amplitude of a sine wave in the presence of noise. And noise is everywhere. So if we have this plus some noise, it's just everywhere. Okay. Fourier transform of the noise, if it's white noise, it's everywhere. But the signal all gets pushed into one little spot, and I can measure that amplitude and ignore the noise.
What
Yeah,
was the point of doing?
to improve your signal to noise. So the Fourier transform is super good
So-
at building signal to noise ratio. Because over here, if you look at this guy, my signal's everywhere in time and my noise is everywhere in time. If I look over here in Fourier land in frequency space, my signal's all concentrated in one spot.
But
So boop, I'll read that
that's
spot.
specifically if you want to measure at one
If,
frequency. that you
if I
know.
want to measure the amplitude at one frequency.
Oh, it's like
Yeah.
the SPET stuff?
Yeah.
Okay.
Yes.
But so for what we're doing now, we don't know what frequency, so this doesn't help, right?
Well, again, in SVET, if you're vibrating at a frequency, then I know what frequency I want to measure.
Oh, when we measure the DC, we're not vibrating, are we though?
That's right. And so
So-
the problem with DC is that, you know,
There is no.
there is no,
Yeah.
yeah, you know, it takes infinite time. If you have a glitch in your data, so what if I have this as my signal and this as my noise? One glitch, you know, one just
Transient.
Outlier.
transient outlier, you know, my A to D converter gave me a 0 for no reason,
Like
right?
cosmic,
Cosmic ray.
rays.
Cosmic fucking ray. Okay. I once made a slide deck at Amgen, another Amgen story called Amgen's Cosmic Ray Detection Platform. My boss was not impressed.
Yeah, so for all I have for Rosnow Bingo is Costa Rica mentioned and Amgen.
Okay,
So.
I'll have to figure out some other things. So anyway, if your signal is a superposition of these, then do you want a Fourier transform in order to find the amplitude? Hell no, because a Fourier transform of this is noise everywhere. And so the Fourier transform is going to just spew noise throughout your domain. Much better way is to you know, if you just have very few glitches, is maybe do some sort of averaging, right? So all right, so anyway, let's get back to it. I just wanted to share that that sort of you know, the idea again that these that in some ways you can think of momentum space as being the Fourier transform of the position space. So momentum wave functions are Fourier transforms of position wave functions. Why is that? Because they have this form.
The trippy,
Yes. So momentum space is a Fourier transform of position space. Another way to think of it is if you have, think about this. This is an eigenstate of the momentum operator, right?
yeah,
Because what's a momentum of this? It's got constant wave number. So
Yeah.
this is an eigenstate. This is an eigenstate of the position operator. Forget the label for a minute, or let me put it this way. This is an eigenstate of the position operator, right? Because where's a particle? It's right there.
yeah,
Where's a particle here? It's fucking everywhere,
yeah.
right? But it's got discrete. In momentum space, it's got discrete momentum. This thing is well localized, but in momentum space, it's got infinite, it's got total uncertainty in momentum. It's got all values of momentum. By
Oh,
localizing the particle here, I've given it momentum, all values of momentum. So my uncertainty in the omega is infinite. I mean, I have maximum uncertainty in momentum, right?
okay.
Because I got maximal certainty in position.
Whoa, okay.
And vice versa, right? So you're sort of seeing Heisenberg uncertainty, right? And furthermore, if you want to really do your best job of Heisenberg, right, then this will be your best bet, is to have a Gaussian distribution for position and a corresponding Gaussian distribution in momentum. Those are the wave packets that will give you these things.
Does he talk about this in Griffiths?
not the way I am.
Okay, I like the way you're talking about it.
So, all right. I'm just trying to give you again
Yeah.
different alternatives because it's not like there's one way.
Yeah.
And if you think that the way I'm saying it is super resonant or, God, why couldn't he say it that way? Well, it's just because you've heard it and read it enough times
Mm.
and so keep at it. So again, the eigenfunctions of P are sinusoidal and with the de Broglie formula, they're not normalized yet. And in fact, uh, they don't live, what am I saying? The eigenfunctions of P certainly do, or I'm saying they don't, oh yes, they don't live in a Hilbert space. So what I mean by that is that it's one thing to say the dimensionality of the space is infinite. It's another thing to say that the physical domain of the space, right? That a sine wave goes on from minus infinity to infinity in x, if this would be x, right? And so that's the problem where I'm saying those are not, one of our normalization conditions for a wave function is or a condition for a wave function to be sort of meaningful is that you can normalize it, right? Can you normalize this thing? A sine wave isn't normalizable in a sense because at least over space it just keeps on going, right? And so you'd like your wave function to sort of go to zero as we reach the ends of the universe, and this thing doesn't go to zero, right? So it's a little bit problematic. And the way we sort of solve that in QM is if you take packets of them, and what's an example of a packet of those things? Oh, right there, the Gaussian packet, right? So if you take the Fourier transform of a Gaussian, again, you'll get another Gaussian. But what it's saying is right that, that that there's some minimum omega and maximum omega, or some minimum position and maximum position for this packet. So if we go far enough in the universe, all the probability is constrained. Okay. And so let's see, eigenfunctions of X are similar in direct notation. So if we project psi onto an eigenfunction X, that's going to equal the integral of x prime x. So I'm using x prime as the identity operator with the dx over here for a continuous variable x. And what is x? The inner product of x and x prime? It's a delta function because x and x prime are orthogonal according to eigenfunctions of discrete eigenvalues are orthogonal, right? And so this guy is going to be the delta function, and this guy we call psi of x. And what is that delta function? So these are continuous spectrum and rather pathological functions. And it's sort of obvious. What do I mean by obvious? That you can build any function from delta x minus x prime. If you want to know what's the value of f at x prime, well, that's going to be the coefficient of, that's this guy, coefficient times a delta function, so you're sort of specifying, here is some function, x and f of x, I have some function, oops, I didn't mean to be multi-valued here. Let me, okay, so we have a function f of x, And it's sort of weird to say, well, I can describe this function in terms of a basis, and the basis is the family delta of x minus x naught, for a whole bunch of different x naughts. So first, I'll pick x naught over here, and the coefficient is that. And then I'll pick x naught over here, and the coefficient is that. And then I'll pick x naught over here, So, I mean, it's a sort of dumb way to say, hey, yeah, I can decompose this function. I mean, this could be a nice continuous, polynomial or something like that. But let's write it in terms of this basis, right? And again, it's an infinite dimensional basis because between any two different x naughts, I can pick another one, right? And stick it in there. And then I just go to that x naught and say, what's the value here? That's a coefficient. So there's a sort of goofy way, to think of parameterizing a function, because normally, you don't want, I mean, y equals f of x. What's the dimensionality of this?
I would think two.
Uh,
There's
yeah,
X, there's Y.
I guess I can see where you're coming from too, but I would sort of say one, right? Because there's one input
Yes,
dimension.
just one output.
Right, and yeah, so the output,
Okay.
I'm not thinking of the output is the function, right?
Yeah,
And so but I could say, hey, but you know what, dude, you're telling me this is a one or two dimensional function, but we can describe it in an infinite dimensional basis. Wouldn't that be cool? So why would you want to do that? Right? And that's sort of what we're doing in quantum mechanics, because again, I mean, the mathematical structure lets us do that. Okay?
yeah.
That each position is an orthogonal component, an orthogonal basis.
When I was trying to ask about infinite dimensions earlier in the class, like weeks ago, this is
Yeah.
what I was trying to ask about.
Yeah, so that's it. It's weird that you say, really, this is infinite dimensional. Yeah, because we're picking, goofy ass basis, and every different x naught is orthogonal from the other one, and so they form linearly independent basis vectors.
Yeah.
So y is the sum of I guess c sub k times delta of x minus x sub k. And discretizing when you could take a limit as well, right? And so, I mean, that's a dumbass way to,
Yeah.
write a polynomial. Hey, you can do it. It's cool. So, so anyway, that's also why, when we look at some of the problems in quantum, you say, why don't we start with the simplest problem? What's the simplest problem? Like the free particle?
Or like in a well, particle in a well?
Yeah, no, you forget the well, free particle, via zero. That should be the simplest. I mean, in a classical mechanics problem, the free particle is the simplest particle, and you can integrate Newton's equation, and yeah, okay. Project, yeah, or, no force keeps on going, right? But in quantum, the free particle is super pathological, because the eigenstates are these delta functions, and it's infinite dimensional. When you start putting walls on a box, as a free particle is sort of the particle in the infinite box, right? Once you put finite walls on that box, you discretize the energy level, so we can talk about xk instead of having this infinite dimensional crap. And so, yeah, the free particle is really sort of pathological. And so, anyway, so these delta functions are what space is made of. It's sort of like, whoa. Um, and so that's that. let's see, problem 3.10.
This is all in Griffiths, right? This last part.
Yeah, I mean.
Why does he wait till chapter 3 to?
Well, again, his idea here is, let's go here. So part one is theory, part two, timed independent. This is our formalism.
Okay.
Okay. And the reason he doesn't give you formalism first is because it's so freaking abstract and
Okay.
weird
I
ass.
guess you have no intuition.
That, yeah, so he first wants to say, hey, we can solve some problems,
I get
some
actually,
meaningful problems. But the first thing we need is a little bit of theory, then we motivate, how simple sort of problems work. And notice again, his free particle is, to his credit, a little bit later. He's not going to start with it because it's pathological. And so now we're going into the formal general description of it. Um, and then the next chapter next week will generalize to 3D, and then we'll do spin, and then multiple particles, and symmetry. Symmetry is where dead mathematicians are buried, isn't it? No, symmetry is.
Mhm.
No.
Where a lot of very difficult calculus problems have also gone to die,
Yeah.
which is kind of nice.
It's also where you find a good lawyer.
I don't get it.
Where do you find a good lawyer? At a cemetery.
Because
Lawyers are evil, so
Oh,
good
okay.
lawyers. Anyway,
That's true, they don't make it.
yeah. All right, so let's see, problem 310.
Or statistical physicists.
Where is problem 3.10? Problem 3.10. Is a ground state of the infinite square well an eigenfunction of momentum? And if so, what is its momentum? And if not, why not? For further discussion, see 344. And so I'm trying to think, what was I thinking when I pointed this thing out? Yeah, I mean, the answer is no. The ground state, nor any of the states of definite energy are eigenstates, because the um, the momentum operator has the wrong symmetry to commute with the infinite well. So the momentum operator, if you think of it on one side, it's gonna give you a positive delta function as at the turning point, and at the other side, it's a negative delta function. And so it's got odd symmetry, and the energy is even.
does that have to do with the commutator as well?
Yeah. Yeah. All right, so we managed to survive and we're out of time. What was the coolest thing you learned today?
I think definitely the thing you were showing with the Fourier transforms. The graph.
Yes, I've never thought of something like that. Like, I've had the tools in my life
Yeah,
for like the past 2 years, and I've just never thought of, what happens if you take a Fourier transform of something,
of a direct
of a
delta.
direct delta?
And you
or-
saw how hard it was to set that up in MATLAB, why I love MATLAB, right?
I mean, you,
Okay, you didn't appreciate it.
happy
It
with
was,
it.
it was too cheesy.
it's my mathematician, my inner mathematician wolf is screaming.
Okay,
Is the
but it gave you the right answer within a
Yeah.
normalization.
I thought it was really cool. That was really,
Yeah,
it was like, I don't know, it's weird because it's an approximation. It's not
so
the
what?
real thing, but it's close
I
enough.
think it,
You
yeah,
know, 10
exactly.
to the minus 16 doesn't, is close enough to zero that it doesn't bother me, but, I
Yeah.
know that that's rounding error of floating point numbers.
Yeah.
So next time I'll give you a little bit of stuff from Penrose and Roger Penrose and we'll try to wrap up chapter 3. And no, we need another week for chapter 3. So next week we'll finish up chapter 3.
Is this week 6 or what week? are we
This
in?
is 7.
Oh, okay.
All right.
Oh, so we're on time-ish, because week 8 is halfway through.
Yeah.
Cool.
This is week 8?
Week 7 right now.
Oh, week 7. Okay, yeah, we're gonna be done with chapter 3 on week 8.
So what was that question you were, interviewed the